bunch of you answered the survey which I sent out, which really helps because it frames sort of context as to what things you might like to hear about and what things don't interest you at all. So we'll try and focus on those today. From what I sent out, pretty much the majority of you have not programmed on a microcontroller before, so a lot of what I'll talk about will probably just go right over your head. So I'll try to keep it as abstract as possible, and perhaps we can just talk about where it might be applicable in the biomedical industry in the years to come. I asked you which industry are you most interested in, and healthcare was the most dominant one, so we'll talk about that. I'll go through a couple of use cases that Kiwi has explored ourselves, and we can kind of talk about the healthcare industry in terms of wearable technology today and where it might go in 5, 10, 15, 20 years, so on and so forth. Okay, so key points that I'd like to address today, sort of an industry to explore, healthcare, the importance of placing a sensor on a person and the accuracy associated with that placement, types of models that can be developed to understand different types of movements or patterns from biosignal data, the limitations of working in an embedded environment, and the importance of testing. So all of these sort of industries here we've explored with Kiwi, but I'll focus sort of on the medical space because that's sort of more applicable to yourselves. The first one is kind of interesting. It's patient authentication. So this can be understood in two contexts. Let's say I'm wearing an activity tracker and my insurance company gives me sort of like a discount on my premium if I walk a minimum of 10,000 steps per day. So I could be like a normal person and I could go for 10,000 steps for a walk, or I could try to game the system and I could put my activity tracker on a dog and let my dog go run around. So where's the discrepancy or the difference in that? That's sort of the patient authentication. What we've done there is with an accelerometer and a gyroscope, you can actually determine the, let's say, the 51st person in a group. So if you have a population of data, then you can determine the outlier of that data and ensure that it is actually that person that is walking day over day. And they're not putting it on their dog or they're giving it to their kid to wear and run around. So the second one is fall detection. So that's it's a pretty well explored use case in the use of accelerometers. And what's possible there is sort of real-time relay of information. So let's say I were to give a little pendant or a wristband to my grandmother and she wears it and it's connected to some sort of smart hub. Anytime that she falls or if she's too stationary for a long period of time, a notification can be sent to my phone. The problem here with a lot of these use cases is getting the elderly person to actually wear the device. So it's user adoption. It's a very difficult thing to introduce a new technology to someone that is gone their entire life kind of adverse to technology, or they prefer to just talk to people or things like that. So that's the largest barrier to entry in the medical space. And the last sort of use case, and probably the highest potential and most applicable to yourselves, is rehabilitation. So understanding movement patterns to better rehabilitate, let's say, athletes or a person that's in a car accident, if they have a certain type of like a strain on the muscle, there's certain exercises that they need to do and they have to repeat them a certain amount of times. You can use an accelerometer and gyroscope device to ensure that those exercises are actually being performed properly. So it can add a lot of value to the practitioner and the person actually wearing the device. So it's sort of a win-win scenario, and they're also a bit more cost tolerant to having a device at, like, let's say, a higher price point that will provide them some value. Or it could be actually included as part of their, let's say, their like insurance plan, what have you. Cool. So now let's talk about accuracy and placement of sensors. So current machine learning models for activity trackers sit between 60 to 70% accuracy in like a real world test. So while I'm wearing this Fitbit right now, as I'm just kind of waving my hand talking to you, it's actually counting steps. And if I were to wear and continuously kind of wave in this sort of rhythmic pattern over, let's say, a 2 or 3 minute window, it would actually presume that I'm walking, not, even though I'm just staying stationary, because they're only looking at kind of a pendulum pattern with your wrist. And if that happens again and again, then you'll end up with this classification state of walking. So really understanding where the limits are, or what does your data model define for the activity you're trying to track. So throughout this, I'll just sort of use walking as the example, because it's quite easy one to understand. There's lots of overlap between different motions, and probably the most common thing that we all do every day. Higher accuracy is needed for healthcare because to ensure, let's say, with insurance or with detection of falls or sort of more life-concerning events, a higher accuracy is needed so that people don't game or falsify something that is there to improve their life. So now let's talk quickly about the location. If you were to place a sensor on the wrist, the positives associated with doing that, you've got sort of a bit more tolerance for the individual because they're able to do something that they're already accustomed to, like let's say wearing a watch. The problem with that is there's a lot of overlapping nature of movement. So if I move my hand like left to right or up and down, that could be very easily interpreted for walking as well, because I could be walking and waving to you at the same time, but it should still detect that I am walking in case. Another location is along the waist. So this is going to guarantee a much higher accuracy, and it's been proven long ago. There's, in a Kellogg's box, you could get a step counter that just has like a little pendulum in it. It's pretty accuracy. The main thing that companies like Fitbit did was basically digitize that step counter that was in a box to connect it to your phone, which makes sense because then you have day-over-day logging of your information. The negative, it's a new habit for people to do, and in any sort of application of technology in an actual consumer space, the hardest thing that you're going to overcome is perhaps encouraging that new habit or that transformation of what you think is the best case for them, and they're going to tell you something completely different. So balancing those two. Do you guys have any questions up till now? Yeah,
I guess actually, so as far as using it in healthcare,
yeah.
Did you get that 85% figure? Like where did you get that?
This is coming from customers I've worked with.
So a customer wouldn't feel comfortable using this unless it was at least 85% accurate?
Yep. So they want to have a baseline agreed upon accuracy under 2 testing scenarios, which I'll talk about later. But the 2 are like a use case specific for their needs. So let's say it's for a senior care home. So they know the majority of the time they're either watching TV, they're walking a little bit, or they're laying in bed or sitting in a chair. Then the use case would context those movements, and as long as the accuracy is relative to sort of that every day-to-day space, then the accuracy is acceptable.
Okay.
They wouldn't take into account, let's say, playing baseball or, I don't know, doing cartwheels, things like that, because it's not really relevant.
Yeah, okay. Actually, I have another question.
Yep.
With the last slide, though.
Yep.
How did you guys value these parameters? I just go ahead and say a basketball free throw evaluation is worth $10 million.
So there's an industry report provided by Gartner every year, and they give overall valuations to industries, and then what we did is we provided a sub-component analysis based on, let's say, percent of population that plays a sport.
Sure.
And then that's how we got these values and determined sort of a market value for it. Anything else?
What about overcoming privacy concerns? Because people may sleep, or they may have some kind of intense activity in the night, couples. So how do you overcome those kind of stuff?
So the way that we found that works really well for privacy is everything is opt-in. So any choice that's made by an end consumer, they're very cognizant that as soon as they choose to share or capture this information, they're opting into it. We always have the option to turn it off or to anonymize that information, but to remove certain events that you might not want to be transparent, it's very difficult to do that. So it's just making sure that each individual person is given upfront the choice to do something, yes or no, and then they can always turn it off. To try and remove every little nuance or to try to protect that, it's very difficult to do, at least right now with the computing power available. All right, let's go on. Okay, fun stuff. Developing a model. So there's kind of 4 steps that are needed. You collect or process original data. So what that means is, let's say 10 of you in this room would wear an accelerometer-based device on their wrist, and they would go walk 100 steps. And then we collect that bucket of data for those 10 people. We have that and have that available to be processed. We would then simulate that data to a larger population based on a kind of known variation in movement. So let's say you have a population of 10, you can make that a population of 1,000 by adjusting those 10 people's variations of steps by understanding that some people walk a bit slower, some people walk a bit faster, some people rotate their wrist more, some people lift their arm up a bit more. Those can all be done with kind of taking that original data and simulate a larger population body. What's done next is you take that same subset of 10 originally and you collect variations in the movement. So let's say I'm walking traditionally, or I walk with my hand in the pocket, or I walk while holding my phone, or I walk holding my phone like this, or walk while holding a bag, or holding my backpack. Those are all variations that you would need to account for in building a data model if it is associated with your defined use case. So collecting that data, and then you repeat steps 1 and 2 to have a larger population of data. And the last step is you would generate a data model, which we'll go into, from that population of data. So really, the bulk of the work in developing any sort of good model is collecting the data and labeling it properly. It's arguably the hardest part. There's a lot of tools available now that can leverage the mathematics side, but having properly collected data and labeled is kind of at the forefront of a lot of challenges in the wearable space for developing good products. Okay, so we'll talk quickly about the types of algorithms that can be used with that data to extract, and I'll touch briefly on the limitations associated with each and the advantages as well. So the first one is pattern matching. This can be used with like a template or something called dynamic time warping. Basically what this is if you have a window of time, let's say 1 second of data, and you label that 1 second of data as walking, then you feed in a queue of data into a processing environment, you're able to match or compare that template of data that you've stored in some sort of processing array to that real-time buffer that comes in, and you are essentially just looking for a match to see the distance in that real-time buffer relative to your template of data, how close they are together. So in the case of dynamic time warping or other template-based approach, the closer that you are to 0, the better the result is, because you've now got a closer match. So that's the essence of pattern matching. It's arguably a lot of limitations with it, because if that template of data is only applicable to one type of movement, then you're only going to be able to account for that one type of variation. So it's very limited. It can yield a very high accuracy if you're looking for a very specific nuance of movement, and then you can extract that from data. So it's very valuable there. So let's say you have an electrocardiogram and you're trying to determine a certain arrhythmia in a heartbeat, and there's a certain type of waveform that you're looking for. You could use pattern matching or dynamic time warping to extract and find those nuanced patterns very quickly. It's also very computationally intensive, so it's not really suggested for real world applications because the battery would drain on the device and things like that. The second one is machine learning data models. So basically what this is taking a series of statistical values from, let's say, a template of data or like a period of information to create a mathematical representation of what that queue of data or segment of data means. So does that mean, what is the average of all the values in that buffer? What is the variance amongst those values? If you have two axes of information, what is the covariance between those two axes? You would use those numerical identities to create essentially features that you would learn a model about. So in the example here in B, this is walking and other movement. So let's say blue is walking and red is other movements. And this axis is the mean or the average of a buffer of different variations of walking, and this is the variance of that buffer. You would plot all of the buffers of the variations of movement on this plot, this two-dimensional plane, and you would create a model that basically addresses this section here as walking and this section here as other movements. And if any segment of data when you're processing falls into one of these two sections, then you would classify that movement as walking or other. The last one is neural networks. It's kind of an extrapolation of creating a data model from features. It allows for, you can think of it like a 3-dimensional space on a 2D plane. So you allow for more interconnections or probabilities for each classification to occur. The mathematics behind a neural network is similar to how your brain processes information. So if you have different points in space and you are trying to, or if you have different nodes in your mind and you're trying to make decisions on information based on the probabilities that rest in those nodes, a neural network is essentially allowing you to create a digital form of those nodes to make classification decisions. So I'm saying yourself, I would classify yourself as wearing a Detroit Tigers baseball cap and you've got a yellow t-shirt on. Great. Those are kind of visual characteristics that I can immediately apply to yourself. You guys have questions about this? Yeah, this is pretty complex. People spend like tens of years studying each of these fields, so or decades. So yeah, the neural networks is kind of the forefront of that work. A lot of things that you might implement or you might encounter in work if you're to create a wearable application in the future, most likely the core mathematics that will be utilized is a neural network.
So like what kind of features do you look for when you're using your neural networks and machine learning algorithms?
Yep, there's a variety of different, you can come up with thousands of mathematical features, but start with, for the purpose of an embedded system, I just try to use as simple features as possible. So using just like a mean, or using a standard deviation of the space, or using like estimate the slope or the average slope of all the values in the space. And the reason that you do that is the complexity of the computations that you perform. Let's say you're trying to only do linear operations, which would be ideal on an embedded system. As soon as you do ON squared operations or ON cubed, you're gonna slow down your system, reduce the capacity to provide a real-time classification, and you'll probably end up with more errors because on an embedded environment or processing information on like a watch, there's a lot less flexibility in error. So you're also, you end up going into, let's say, are you using fixed point implementations? So the accuracy degrades if you use more complex features. So on the 10,000, like 0.0001 decimals, if you cap at that, so there's some mathematical features that you need to the millionth sort of space. So balancing with more simplified features first, and then you can kind of increment to more complex as you go along.
Actually, another
Yep.
question. I know, like with machine learning neural networks, like if you're like on a regular computer, like a typical language would be like Python using different libraries and stuff. But for embedded systems, since it's much smaller, like I would imagine you can't have like such a high level language. Like you probably use like C and like assembly to like get around like your resources. So how do you like go about using machine learning with like
Yep.
simpler libraries if you use simpler
Yeah,
libraries?
so you can use like a Python library or like scikit-learn to train a data model. Then basically it's just understanding the math well enough to create a C library that allows for the processing of that data model that you create. So you create and train the data model in your server environment with the standard tools from scikit-learn or wherever, and then you have to transcribe the outputted data model to the embedded environment. And that's the main value that Kiwi provides. That's what we do, is we train these data models and then we create custom C
So you like
libraries.
take all your data from your devices, send it up to a server, and like send it back. So like if you don't have Wi-Fi or like an internet connection or something, can your device still like?
No, so we'll make like a static library that goes onto the embedded device, and then we can update that static library on some periodic basis. Let's say it's on a monthly basis or year. People don't really care after you've got the base accuracy there, so maybe you do one update after or something.
Gotcha.
Yep.
Maybe in terms of, if we are looking at using this prototype as a future real-time transmission of data for, say, disease diagnostics or
Yes.
A dynamic monitoring of specific parameters.
Yes.
How would you go about choosing the percentage of training data in a real-time fashion
Yep.
with respect to the test data and the validation?
Yep, we usually try to use an 80-20 rule.
It's always.
It's roughly that. 80% training, 20% testing. And then we'll do, so that's on like the server environment testing, but the more valuable tests that occur are the real world tests. So you can test as much as you want in like a server environment, but until you actually get people to wear it and see how it really performs, then there's no real, the value gets decreased and decreased the more you just try to live in a simulated environment. So any advice I could give to you guys, things that you might know, do real world tests as quickly as possible. Anything else?
Like one quick question. You said you graduated in like 2011. Was that like a bachelor's or like your master's or something?
I did bachelor's.
Okay, so then since you're like the CTO, like I'm guessing you kind of implemented all the machine learning stuff. Like where'd you go about learning it?
I've been programming since I was maybe like 6. So this is just like something of interest. Okay. 3B. So algorithm development. So we sort of touched a bit on this, so I'll go over it a bit quicker. There's 3 main steps to developing an algorithm. First step is filtering data. So you can use filters like low pass, band pass, high pass filters to remove noise along a certain frequency. So if you know there's a certain operation that's occurring, or if you want to remove slight jitter from a movement, like bouncing your wrist like this, you can almost remove that noise completely by using a filter. So that's the first step that we applied to data, and we define that filter. The second is feature extraction, so it's coming up with those features that will describe that segment of data. And the last step is generating a model based on those features. So here, again, it's just different clusters of data based on 2 features. And then each of those features are, one of them is like a low pass filter with a mean or like average of data, and there's certain plot tendencies. Then we take those plots and generate a cluster to, or a kind of region that is applicable to those plots. The overview, oh, and I guess our other customer, which is a much longer lead of sale, is new product development teams. So let's say there's a company that's looking to make a smart version of a piece of sports equipment. Let's say it's Bauer Hockey, they're trying to make a smart hockey stick. Then we would be providing this toolkit of kind of machine learning and sensor recognition tools to them to create their new product, but their product life cycle for these R&D teams is like 2 to 3 years. So it's very long lead. You have no control over when they're going to release a product and what might be the drivers for actually releasing that product. To overview what does the company do every day and the accomplishments achieved. We're a very results-oriented company, but very mobile. So we just ensure that we issue builds, we test them, and then we release them to our customers as quickly as possible. Probably release, on average, 2 builds a day to customers. Just because now we've got the core of our technology built, a lot of it is just testing and kind of intaking data, or collecting more data, intaking it, building a model, transcribing it into an embedded environment. So the process is pretty fairly concise, so we can do that pretty quickly. Who are your clients in the healthcare field? What are the most common variables that they want to measure? So a lot of healthcare use cases that we've explored, we've done very short kind of test case projects with healthcare companies, but the roadmap, or the product roadmap for them, and us being a startup, is too long. So they have, a healthcare company might have a product roadmap or an interest in creating a smart activity tracker for nurses, let's say, or nursing staff, but their timeline to implement is 5 to 10 years. So as a business, we can have a small like education conversation with them, but the focus of our time is on activity tracking and sort of health and wellness applications. So new product companies, or these semiconductor businesses, which are actually putting new microcontrollers in the market, they release microcontrollers twice a year, and they're trying to release new microcontrollers with sensor recognition in them now. So that's because of that. I would imagine we'll come back to the healthcare space in maybe a couple years, be more focused on that. How do you combine with prosthesis design? We're not currently doing that. It's very costly to do that. There's a company in Toronto that's kind of interesting that has gone through this. They started in 2012. They're called Bionic Labs. Yep, 2 smart guys as well. They started from Ryerson University, and they built, they're now a publicly listed company on the TSX, so that's kind of interesting. But they haven't released a product to the market yet. Pardon?
Is it Able Bionics?
No, Bionic Labs. Okay, how does Kiwi differ from all the accelerometer, motion-based fitness activity trackers on the market? We only provide the software. So we're not a hardware company, we're just doing the sensor intelligence. Is Kiwi looking to incorporate its technologies with the upcoming virtual reality gaming industry? Yeah, it's arguably one of the most kind of enjoyable or kind of fun things that we can explore. We'll be doing an interesting like mixed reality demonstration demo at CES. that mixes movement and biosignal patterns. I can send you guys a link of that video when it's available. But keeping that pretty under wraps for the moment. What kind of skills and qualifications should a potential employee have to work for your company? We're pretty focused on people that can show things that they've built and demonstrable outputs. So anyone that we've hired to date has basically come to us with something that they've worked on personally in the space and really cared about, but they've shown that they're able to apply their knowledge very concretely in Proficient. And yes, we tried to build your own motion activity tracker. How can we get started? We have like a developer version of our library available at this link. It only works with Android or iOS phones, and it just tracks a bicep curl, but it's something quick that you can try out and test with if you're really interested in building something. Cool. You guys can email me questions if you have them, and yeah. You guys have any other questions?
So you said that your company kind of focuses on like the software of like getting sensor data and then like algorithms like generate patterns and models from those. Do you see yourself like branching out from activity tracking and just using your like expertise and general like sensor recognition for other applications like in the future?
Oh, totally. Yeah. So like that's I've got a wide variety of those explorations. We did an interesting one around understanding color patterns from an EEG sensor, so how a person stares at the colors red, green, and yellow, and being able to differentiate those. So anytime you stare at the color red, what are the, let's say, show you a gradient of different colors, capture those signals, and then also use trigger words to see how your brain responds to let's say things that are colored red. So if you say red car, if you say apple, if you say red slushy or things like, or cherry slushy, those things give off a certain signal, which are also indicative or descriptive to the word red. So we built a model around that, and what we found with the current resolution of sensors today, you're able to build, let's say, a 70% accurate model on an individual by individual basis. So you'd have to go through this training process for each individual person, and then it would work for you, but it couldn't be generalized to like the entire class. That's just where it's at today. Anything else?
You guys were like in like EEG sensing. Like, did you guys like kind of make your own, or did you buy one?
We just used, there's a couple different companies in the market. There's one called Cognionics in San Diego. They make more medical or a bit of a higher grade EEG helmet. Then there's Muse in Toronto. They have like a little headband that's like $300.
Yeah.
Yeah, sure.
So like I get that there's probably like a really difficult timeline for you guys to operate with, like within the healthcare industry. Are there like, is that like generally the case that you've seen with them, or like are there things that they're willing to implement like relatively quickly?
That's generally the case that I've seen. To actually end up with an end product that is used by patients or healthcare practitioners, yes. Might be a bit more flexible on like data entry software. So if you were to just create some sort of software that a doctor could log information into, might be a bit more pro. But as soon as it becomes something that people have to wear or things like that, then you've got a product life cycle to actually get that approved by the FCC, and there's medical clearances and things like that. So it takes
it's a little bit of a personal question.
Sure.
Did you go straight into this right after graduating?
Oh no, I did a few things, a few different experiments. I worked in the film industry for like 8 or 9 months just for kicks, something I've always wanted to do. I tried to start another business around understanding heart rate and skin resistance patterns to have movie experiences catered to you based on your biosignals. So like a choose your own story, but based on your emotions. Yeah. A bunch of other stuff too, but those are probably the most applicable to this. And the reason that the film industry is really applicable is it's understanding people in, like I came from a technical background, but I didn't have a good understanding of how people in the arts or in the art space interact and work with each other and things that might not be as technologically, like they're not as cognizant of the engineering side. So to have a good understanding of that kind of complementary environment, I wanted to have sort of a balanced view to the world. So that's the reason for that.
So if you're looking at hiring a full-time employee or co-op students, we would like to extend an invitation to come and visit us on 23rd of November this month.
Okay.
Just 3 weeks from today. There are about 32 groups. We'll be giving a demo of different prototypes.
Okay, cool. All right, I'll do my best. I may not be here, but
So somebody.
yeah, I'll see if I can send something as well. Follow up next week.
So like right now in your company stage, like are you looking to hire, or are you kind of like set with like your employees now, and
Our employee pool is set for until I would say May of next year.
so May 2017?
May 2017 would be the next time that we would look to do any hiring.
It's not great.
Or, do you guys ever use like mocap at all? Like, do you guys ever use like motion capture systems like Xbox Connect or something like that? Or?
Oh, like the visual motion capture.
Yeah.
Yeah. We have explored with. We've done that. I guess we've done head tracking.
Okay.
That sort of just understanding like people's faces and places like that. But a lot of that is it's a bit too big brothery. It's a bit weird, man.
Yeah.
You gotta like a balance of
Where you put that?
yeah, where to put that. So
Yeah.
try not to spend too much time on it.
Still like it.
All right, please join me in thanking our speakers.